Miles beneath the surface, there are toxic underwater lakes that act as permanent graveyards. When a marine animal crosses into one of these dense brine pools, its system instantly goes into shock. These pools contain 5 to 10 times the salinity of normal seawater. They are entirely devoid of oxygen, filled instead with a lethal cocktail of hydrogen sulfide and methane that essentially marinates any creature unfortunate enough to fall in. Yet this hostile environment is a near-perfect reflection of what the primitive Earth looked like 2.7 billion years ago, before our atmosphere had a breathable mix of gases. These organisms show us exactly how biology adapts when its most basic requirement, oxygen, is replaced by the harsh chemistry of the deep Earth. For decades, biology has relied on a rigid rule: oxygen is produced by photosynthesis. Organisms like these cyanobacteria use sunlight and water to generate the oxygen that makes our planet habitable. But in 2013, marine scientist Andrew Sweetman initiated a routine test in the Clarion-Clipperton zone of the Pacific Ocean. He dropped a benthic lander 13,000 feet down into total darkness to measure how quickly deep-sea life consumed whatever oxygen drifted down from the surface. This graph illustrates the expected decay of deep-sea oxygen over time. But Sweetman's sensors did exactly the opposite. In an environment totally cut off from sunlight, the oxygen levels were rapidly rising. The data was so anomalous that Sweetman initially assumed his equipment was broken. He spent years running rigorous tests with different sensors, even using mercury chloride to kill any hidden, unknown microbes that might be skewing the results. The oxygen kept rising. It was purely abiotic. The production of oxygen without a single living organism or a single ray of sunlight breaks a core assumption of Earth's ecology. The source of this impossible breath was resting right on the ocean floor. Millions of square kilometers in the Pacific are blanketed in polymetallic nodules. These are small, potato-sized rocks naturally rich in manganese, nickel, and cobalt. To find out how these rocks were behaving, Sweetman teamed up with chemist Dr. Franz Geiger. They retrieved the nodules and placed them in sealed, chilled laboratory chambers that perfectly replicated the freezing, high-pressure, ultra-salty environment of the deep ocean. They realized the nodules contain a very specific chemical geometry. Manganese acts as a positive terminal, while iron oxide serves as the negative terminal. Submerged in the rich electrolyte of seawater, the rock functions as a natural geobattery. When the team attached a voltmeter to a single stone, the reading jumped to 0.95 volts. Now, 0.95 volts isn't quite enough to trigger a major reaction alone, but because these nodules are packed tightly together on the seafloor, their voltages combine. Once a cluster crosses the 1.23 volt threshold, it triggers electrolysis. The rocks literally shock the surrounding seawater, splitting the H2O molecules into hydrogen and pure, breathable oxygen. We are looking at billions of natural electrical engines running continuously in the pitch black, providing an unknown amount of life-sustaining oxygen to the deep sea. But those exact same metals, manganese, nickel, and cobalt, are also the critical components needed to build modern electrical batteries. Estimates suggest the Clarion-Clipperton zone holds roughly $16 trillion worth of these nodules. Extracting them requires dredging the seafloor. In the 1980s, an early test mining operation dragged equipment across a small section of this habitat. Today, 45 years later, the marine life in that specific trench has still not recovered. The ecosystem is exceptionally fragile. When Sweetman and Geiger published their findings, the corporate response was aggressive. Mining conglomerates, including the Metals Company, who ironically helped fund some of the initial ecological research, actively tried to discredit the dark oxygen data to clear the way for commercial dredging. Other independent scientists have raised valid questions about the study, noting that the lab experiments didn't perfectly match the extreme pressure of the ocean floor, and that the expected levels of byproduct hydrogen haven't been thoroughly measured yet. But the risk of ignoring these findings is staggering. Rushing to prematurely harvest the ocean floor for green energy components means we could be destroying the deep sea's primary mechanical lungs before we fully understand how they work. The implications of abiotic oxygen stretch far beyond the Pacific Ocean. When astronomers search for exoplanets capable of supporting life, they primarily look for planets in the Goldilocks zone, where a star's heat allows for liquid water and photosynthesis. Dark oxygen severely weakens that criteria. It proves that an ecosystem requires only water, extreme geological energy, and the right combination of minerals to produce a breathable environment in total darkness. This puts the frozen moons of our own solar system in a completely new light. Jupiter's moon Europa hides vast subsurface oceans beneath a thick shell of ice, entirely isolated from the sun. Saturn's moon Enceladus is actively firing massive plumes of water vapor into space, driven by deep hydrothermal vents. If polymetallic geobatteries exist in these alien oceans, they could produce the exact chemical cocktail needed to sustain life. These oxygen-generating rocks turn the deep seafloor into an active laboratory, preserving the same chemical conditions that likely birthed the first living cells. Dredging these habitats for minerals risks destroying the very evidence we need to understand whether life can exist in the frozen oceans of the outer solar system.